All right.
What are we up to today? 14.
All right, so here's a sign-in sheet. You don't have to actually sign in. Just fill in the little circle next to your name, please. There is no place to sign in, so. All right, so first of all, service learning project proposals, which were due Friday. I'm still missing those from a number of students, so please turn in your proposal and let me know if you have questions about what the SLP is all about and what the proposal is about. Because that's the first step in something that's going to be a year-long process. If you're here for more than just a quarter, you're going to be doing SLPs in 224, 222, 223. So I gave you some feedback. If your proposal looked fine, then you don't need to turn in a version 2 or a version 3. So I set up 3 versions on Canvas to turn in. 10 points, 10 points, 5 points, right? So if I said, no need for version 2 or version 3, you're good. Just run with your SLP. But if I had any questions or needed clarification on something, I put comments in there, and I did not put in a grade. Okay, so make sure you are reading your comments on assignments. And I wanted you to cut off the top of this and just turn in starting from here. Had more than one SLP proposal dated in the future, and I'm not sure what's up with that. But I have one from November and one from December 2019, which was interesting. They weren't time travel proposals though, because that would have really freaked me out. The main thing that was missing from some people, so what I wanted you to do was fill in this part and tell me what your measure of success would be for your given milestones. And so have an outline for this project consisting of a flow chart for the code and a block diagram for the circuitry or something like that. So some of them I just said please fill in the measure of success column. Other than that, the projects sound really good so far. I'm still working my way through them. I've got about a third of them left to do, but they're sounding very interesting so far. So I'm excited to see where you go with them. I changed some dates on Canvas since I'm a little bit behind on reviewing the proposals. So I think the version 2 revision was originally due Wednesday, and the version 3 was due Friday. And since I'm behind schedule, I pushed those back. So if you need to do a version 2, that's due on the 21st, which is a week from today, and then the version 3 would be a week from Wednesday. So, but hopefully you do it sooner rather than later. But if I haven't reviewed your version 1 yet, then I will try to get to it in the next 2 days. I probably won't get to it today. All right, so keep going forward with that. Any questions on the SLP based on feedback or just sort of in general, what the heck's going on with it? Okay. All right, so what about PA2? We haven't talked a lot about this. We've been doing some ODPs. I'll show you the latest ODP solution. And we're taking a break from ODPs for a few days. But questions on PA2, your stick program in C?
I don't have a question on the program, but would it be possible for you to go over pointers and
Oh, yeah, definitely.
input from
Okay, definitely. How many people didn't sign in yet? All right, yeah, let me go through ODP 412 and then let's generalize that into a pointer review. So 412 was processing command line arguments for PA2. And I messed up when I did this. So for 411, you were required to parse your input and know if it was exactly an integer, and if it was followed by something other than just an integer, that was supposed to be a syntax error. And everybody got that nailed down for 411, and we were supposed to do that for 412, and I had modified the code, but I failed to link it together into the test bed. So the test bed was using last year's notion, which was if you put in an integer followed by other stuff, that's a valid integer. And a number of people managed to kind of reverse engineer what was going on and figure that out. But that's my bad, and it was goofy. So if you did anything for ODP 412, I actually gave you extra credit. So everybody got 125% on that instead of 100. Because I know you wasted some time. Well, it wasn't wasted, it's good debugging. But you spent some time trying to figure this out about the ODP. So, so that was my bad if this happens. So let me show you the correct version of the ODP. So it takes argc, argv. If argc is not 2, that's an error right there. Okay, because you're supposed to have exactly one command line argument. If you know the argument is present, then you can go ahead and parse it. So you use your scanf, use the %d, %s trick, and make sure that scanf returns 1, meaning there was an integer and nothing after that. If it's not 1, just return -2. That's a syntax error. If it is an integer, see if it's less than or equal to 0. This was the other thing. Positive number always means bigger than 0. Okay, negative always means less than 0. If anybody tells you otherwise, they're being very casual with the definitions. So positive is bigger than 0. So if I is less than or equal to 0, it's not a positive integer. That's an error, -3. Otherwise, just return the integer. So a few technical issues on that. So let's review this business of pointers. Let's try this with code. All right, character C, we know what that does. C is just a character, right? Char star C pointer or char star space C pointer, right? Spaces are irrelevant. C pointer is a variable that points to a character. This is another way of saying that this is an address. It's a memory address. So C equals quote A, that takes the ASCII code for A, which is 65, stores that in this byte of memory that we're referring to as C. And then C pointer equals ampersand C. Ampersand C says, give me the address of this variable. Tell me where this variable is stored in memory. That's what it sets this variable C pointer equal to. So I'm going to compile with a -G switch. And -G is the switch you use when you want to debug a program using a program called GDB, the GNU debugger. So I've been wanting to talk about this anyway. This is as good a time as anyway. So GCC-G says include debugging information, and we can use that to run GDB. So I'll do my GCC-G, and now I'll say GDB in the name of the program. And instead of running my program, I'm running this other program called GDB, the GNU debugger. All right. So a debugger is a tool that basically executes a program for you, but lets you execute it, say, one instruction at a time. And I can just say run, and it'll run my whole program as if I had just typed the name of the program. But I can also say things like step, which will say execute one instruction, and then come back to this prompt from GDB. And it lets me step through the program, one instruction, one line, one function at a time. And I can also do things like look at the values of variables, or change the values of variables. And it's a alternative to taking your code and, say, throwing in a bunch of print statements to see what's happening as your program runs. This lets you step through it in whatever granularity you choose and look at the values of variables, ask questions about the state of the system, and so on. And it's a really powerful way to sort of work through code that's not working correctly and try to pin down exactly where the issue is. It's also a useful tool for exploring things, for, say, playing around with pointers. So I'm just going to say start. That's how you always start things off. And if I say list, it'll show me my source code. Okay, that's only available because I did the -G switch. And it's telling me it's got a temporary breakpoint at line 3 of go.c, which is my curly brackets. So it's about to start executing my program for me. So I can say step. Well, let me just say next. Okay, so it shows the instruction it's about to execute. Okay, it's ready to execute line 7, c equals quote A. Now I can say print c, and it tells me c is a 0. And if I think of it as a character, it's character \000. That's just the ASCII way of representing character 0. But it's about to execute this instruction that says c equals A. So I can say next, and now it's about to execute instruction 8. So presumably it's just done instruction 7. So if I print c, now I see c is equal to 65. And it's telling me that's the same as the ASCII character A. If I print C pointer, it's equal to 7FFF blah 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 E640. If I print &C, it will show me the address of character C. So C is apparently stored at 7FFF E54F. And so let me start making what we can call a memory map. Let's draw a picture of what this program's memory looks like right now. So I guess I should count these F's once. I'm thinking there's 7 of them. There's 7 of them. So 7F E640, I don't know what that is, but that's what C pointer happens to be pointing to right now. Yeah?
So does that represent an address in an array?
That's an address in memory. And memory is basically an array, right? But that's if you actually looked at the memory of the CPU, at that address, right, which is a 64-bit number, because that's a 64-bit processor, at that location in memory, this is what you find. Yeah?
So I was thinking why they are not the same address.
Those two?
Yeah.
Because I have not yet set C pointer equal to &C, so instruction 8 hasn't been executed yet.
Oh.
Right, after I say next, then they should be exactly the same number.
And then, why when you print C first, why C equals 0? Because you have already given capital A to C.
So the instruction it shows you is the next one that's going to be executed. But same thing here, this hadn't executed yet, this was about to execute. When I said next, that's when this assignment happened. And then C changed to 65. All right, so 7F, E5, 4F, that's got a 65, and that's what we're calling C. So let's go ahead and say next. So now if I print C pointer, it's equal to 7F, E5, 4F, right, the address of this variable C. I can print ampersand C pointer and I get a totally different number. I get 7FFFFFFF E550. All right, so I can use X to examine memory. All right, so I'm looking at memory 4 bytes at a time. And this address has these 4 bytes. So this is address 4C is a 55, 4D, 4E is a 00, and 4F is 41. Okay, 4F, that's our character C. Okay, so this is the byte in the whole, however many gigabytes of memory this machine has. This is the byte that corresponds to the character C, right? The variable C, which is a character. This is where the variable C pointer is stored. It's this 4 bytes and this 4 bytes, okay, 64 bits, starting at E550. And the contents of C pointer is this number put together with this number, 7FE54F, which is the address of C. Okay, so what does all this mean? Here's a location in memory we're storing C pointer. The value of C pointer is E54F. At location E54F, we're storing a 65. That's the variable C, right? The value stored in C pointer is exactly the address of C. So if I use the notation star C pointer, it's going to say, okay, what's the value of C pointer? It's E54F. That's not what I'm looking at. I'm looking at the thing stored at that location in memory. That's the character A, the value of C. So I can print star C pointer, right, and that's our good old A. So that's what's going on at the hardware level, right, down at the level of the memory. And there will be times, not so much in this course, but definitely in 222, when this is how you're going to be debugging your program. Because in 222, you're going to be making data structures, big chunks of memory with all sorts of organization internally. And it's not going to be stuff that you set up when you compile your program. It's going to be stuff that gets created while your program is running. Right? Right now, if we want an array, we say, you know, integer array bracket 200. 222, we're going to create the stuff while the code is running. And the only way you're going to be able to know what got created and what's sitting in your memory is by going into the debugger and sort of looking at memory like this. So we'll play with this a lot more in 222. And it gets really sort of nitty gritty, and if you like sort of working with like tiny little puzzles that get really complex, this will totally be your thing. Yeah?
Yeah, can you explain that, you said for 55C, C equals 41, what does that mean?
54C?
Yeah.
So this address right here, 4C corresponds to hex code 55, 4D is the next byte, 4E, 4F is actually 41. So let's see if we can do examine byte, this thing. Right, so that's the contents of 54C, this is 54D, 54E, 54F, that's your character A, ASCII code 41.
Okay, so why 41 is 54C?
The way that these are stored, and this gets into another issue, if you see an address and you see a multi-byte number, that address corresponds to the least significant byte. Right, so 4C is this byte on the right, 4D is the next one, 4E is the next one, and 4F is the most significant. And it just has to do with this idea that things can get packed two different ways. If you're storing a 4-byte number and you want to store it at address Q, do you store the least significant byte and next, 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 or do you store the most significant byte, least, least, least? And on this system, it stores the least significant byte at that address, and it increases. That gets into something called big endian versus little endian, which end of the thing gets stored at the given address, the big end or the little end. And that gets into religious wars on Stack Overflow and such too. All right, so that's kind of nuts and bolts level. What does this mean practically for us? So you declare pointers by saying thing you want to point to star and then the name of the variable. You can find the address of anything by using an ampersand. And you can resolve a pointer, find the thing that it points to by using an asterisk in front. So I could do something like this. Right? I don't know if it'll compile. But this says take the variable C, give me its address, that's what the ampersand does, and then tell me the thing that that address points to. Well, that should just be C, right? Right. And there's no reason to write star asterisk, but I mean, that's basically what it means. Ampersand star is a different matter. Technically, that should do the same thing, but if we actually try to say, if we just try to do ampersand C, it's not even going to let me compile it. But if it let me compile it, it would be trying to look at basically what's at memory address 65, because that's the value of C, and that would be a segfault.
So like star C, what does that mean?
Star says, what does it point to?
So C is a kernel, so what does it point to?
So that's why I wouldn't let me compile it, because technically characters don't point to anything. But if I did something like this, right, and it will definitely complain about C equals quote A, but I think it will let me do it. Yeah, it gives me warnings. But if I run that, that's seriously going to segfault. Right? Why? C is a pointer to a character. I've basically set C equal to 65. So when I say asterisk C, I'm saying go to memory location 65, tell me what you find there. And memory 65 isn't a valid address. So it gives a segfault. And And the most common error you're going to bump into is just something like this, where C is a pointer to a character, but you haven't given it a value. And if it's not initialized, there's a good chance it's equal to 0. And 0 is not a valid memory address. Alright, so in this case C is not 0, but it is something kind of weird. Very strange. Alright, so questions about this?
Not really about this, but in the ODP, it took car star star. Can you explain the intention?
Yeah, so I'm just putting that in so there's something in there. So let's look at main. And let's debug it. And P is just a shorthand for print. GDB, you can type any command. You only need as many characters as you need to make it unambiguous. So if I say P, it means print. So I can print out argc. Argc is equal to 1. Well, it's also telling me when I start my program, argc is equal to 1. Okay, argv is this big, long, horrible number. So let's examine what's at that location. And it's 7FFF E978. Okay, argv is a car star star. So right there we know argv is not actually anything by itself. It's an address. It's a pointer to something. Okay, so let's see what's at this location that argv points to. And, oh, I didn't expect that. Oh, okay, hold on. Okay, so there's argv. Let's look at the thing it points to, okay? That's the thing at location 7FFF E978. And it's something, right? What is that? That's the program that's running right now. Okay, so it's the full path in my directory, and it's the program name at the end, which is just called Go. So argv is pointing to a string. Okay, hold on. All right. So I'm using the run command inside the debugger to run my program, but I'm putting command line arguments on it. So I'm saying run, and then I'm saying this is a test. Okay. So it's about to execute my program main, right? It's sitting at this print statement. It's telling me argc is 5, argv is this number. Okay. So let's look at argv. It's that number that it's telling us. That's supposed to be a pointer. Okay. So let's see what it points to. It points to this thing, 7FFF E969, which is followed by 7FFF E98A, which is followed by another address, another address, another address, and then a 0. So argv is itself a pointer, and it's pointing to a series of addresses. The first address that it's pointing to, this E969, has a bunch of ASCII code in it. So if you break out the ASCII codes here, this is going to be the /home/nic/CSE224 and so on. It's the ASCII code for my first argument. If I look at this second address, E98A, that's more ASCII code. That's the ASCII code for THIS and an all terminator. Yeah?
So the first one point to that address, so that address should have run, right?
No, because the program name is actually Go. I said run because I'm inside the debugger.
So
But the program name is actually Go. So let's go back and examine that address, but let's say examine as a character, /home/nic/files/224/pointers/go null terminator.
I thought it should point to the run. This is a test because we like RV1. It should be the first
argv1 would be this.
Yes.
argv0 is the name of the program, and even though I said run to start it, I'm inside the debugger right now, and I said gdb go, so it knows I'm running this program called Go. So that's why argv0 is Go.
I don't understand.
Run is just a keyword which says go ahead and execute this program, but it's executing the program named Go. So that's why the first argument is the path to the file Go. Run is just a keyword to tell the debugger I want to start running this program. Okay, so argv points to some location in memory. And what you find in this first location is a pointer to somewhere else in memory, where there's the name of the program. And the next location in memory points to another spot in memory which has the word this is test, and then this entry was a 0. So argv is itself a pointer to something. What is it pointing to? It's pointing to a car star, which means the thing argv is pointing to is itself a pointer to a character. So if we go to the location stored here, we find the ASCII code for that slash. If we go to the address that this has, it's the ASCII code for a T, and so on. So car star star argv is like saying argv is an array of car stars. Well, what's an array? It's just a succession of whatever type of array element you have laid out in memory one after another. So that's a car star, that's a car star, that's a car star. And what a car star is an array of cars. So it's an address where we find a succession of characters stored in memory. Right, that's what we're seeing here. And if we look at the next entry as a character, it's THIS null terminator. So that can be a little weird, right? It's two levels of indirection. For this course, for the most part, we don't really have to understand it completely in terms of memory pointers pointing to other memory pointers. We can really just think of argv as an array of strings, right? So argv is just a plain old array that has elements 0, 1, 2, all the way up to argc -1. And this is the name of your program, this is the first command line argument, second, and so on. And so an important thing when you're working with this is make sure you don't go out of bounds of the array. And how do you know that? Make sure you don't index with something bigger than argc minus 1. So if argc is 1, the biggest element is 0. If argc is 2, the largest element in the array is element 1. If argc is 10, you can access all the way up to argc bracket 9. Right? As soon as you try to go beyond that, you're probably going to encounter a 0. And if you think that's pointing to a string and you try to print it out, then you're looking at a seg fault. Because 0 is not an actual memory location. Yeah?
So how do you know what your limits would be for particular type of,
So for this array or for these arrays?
the first one?
For this array, that's what argc tells you.
Okay.
So if argc is 5, I know that I've got 1, 2, 3, 4, 5 entries in here that should all be valid strings, pointers to characters. But if argc is 5 and I try to look at the 6th entry in this array, I'm risking a seg fault. So when main gets called, main is called with argc and argv. Right? And argc is set up specifically based on how many things have been populated in this argv array.
I understand that further. I'm thinking of seeing some tables where for different types of, I think variables, there's different limits of.
Like how big they can be.
I'm not saying I'm this right.
Okay.
Talk to you about it later.
Okay, so one thing to keep in mind, these arguments are always strings, right? They're just character arrays. Whether it looks like an integer or a double or a string, it's always just an array of characters, which is why we have to use things like scanf to change them into integers so we can actually work with them. But these are just strings, and the system will make sure that this goes somewhere where there's enough memory to store, argc worth of strings, or the address of argc strings. But yeah, catch me later if there's still a question there. All right, so does this make some sense? So like I say, for 224, mostly we can just think argv is an array of strings, and we just grab argv 0, 1, 2, and treat them like any other char star. We can do string length, we can print them with a %s, or whatever. You can also examine /i and actually see like the assembly language code corresponding to your program in this case. So that's some of the stuff it's about to do if I let it continue. And that call Q is probably a call to printf, because that's what it's really working up to. So it's loading some arguments in, and then it's going to call printf. And then that return Q at the bottom is probably the end of my main program. That's main plus 33. So that's the actual assembly language version. And if you try to reverse engineer code or something like that, this is one way to do it. All right, so this was how we hacked Rogue when I was first playing Rogue, because we didn't have source code. You got source code now, though. So. All right, other questions about that? There should be a link on Canvas to GDB, to a little video I made years ago. And like I say, we'll use it a lot in 222. It'll be absolutely essential in 222, but it can actually be helpful in this course for debugging C code, because it lets you, step through methodically. And if you're getting a seg fault, you can just keep stepping until you get to where it says a seg fault, and now you know where that error is actually coming from. And then you can rerun your program and stop just before the seg fault and start looking at the values of variables and say, oh, I'm trying to grab this element from an array, but this element's got a ridiculous value because I used the wrong variable name or something. All right, good. So let's just talk a little more Linux, because I've kind of skipped over a lot of Linux stuff for talking about C. So let's talk more Linux by itself. So we haven't really talked a lot about the file system. And you know, if you work on Windows or any other operating system, you know about file hierarchies. There's like directories and there's subdirectories underneath those, and those can have subdirectories and so on. Same thing in Linux. So let's do this on the server. So pwd shows you your directory. My directory is /home/nic. Presumably home is some sort of directory somewhere, right, or a folder if you like, that contains a directory named nic. If I want to see what's in there, I can say ls/home, and there's all the directories inside the home directory. And there's one directory for every student in this course. So that's where each of your files lives, is underneath, you know, the corresponding directory. Izad should have one. Yeah, Izad's got one over there, and I've got one, and there's a few oddballs like test is set up there, and Goblin King, and everything else is a student. So I can say ls-l/home and get a longer view of it, and you can see things like how much space is being used by the directory. Well, it's 4096 for all of them. The last time that the directory was changed, so you can sort of see the last time that anything was done. So let's see if Izad's been keeping up. He hasn't done anything since August 2016. Which I think was when I set up the server. And there's permissions, and these permissions are mostly just read, write, execute for the owner and no access for anyone else. My top level directory has read access because you have to get to the assess stuff. So I can also cd to /home and just say ls and see what's in there. And /home is not a top level directory. It's actually sitting underneath a directory called /. And so I can cd to / and do a list, and there's what's in the actual top level. So there's a /bin, /home, /etc, /boot, and so on. So that's the root of the file system, is just /. And every file in the system sits inside this directory or a subdirectory of /. And if you're here and you say rm-rf star, that wipes out all the files on the system, because everything is rooted underneath there. But if you try to do it, you'll get a permission error. So different directories. So bin is where a lot of the executable programs are. Okay, bin is short for binary. That's where the runnable code goes. So if we say ls bin, it's got tons of stuff. So it's got ls, it's got rm, it's got echo, it's got remove directory, make directory. All these commands that we use in Linux, bash, they're just programs, and they're sitting under bin. And there's a lot of files here we never use, but cp for copying and so on are sitting under /bin. Boot is an area where system files exist that are needed for actually bringing the system up when you first power up. And that's usually an area you don't mess with too vigorously, but it's got different versions of the Linux kernel and so on and so forth. Dev is where the devices live. So generally physical or almost physical pieces of hardware. So TTY is your teletypewriter. That's what terminals used to be called. That's your, in this case, my input and output, my keyboard and my screen. And if I say copy my bash rc file to /dev/tty, it shows up on my screen, because /dev/tty is my screen. When I output to it, it's my keyboard when I input from it. So this is this idea that most things in Linux are files. Okay, there's a file called /dev/mem, which used to be your memory on your machine. There's an encrypt file system for encrypted file systems. There's a random, which is a pseudo device that is used for generating random things, I believe. PPP for point-to-point protocol. FD is a floppy drive, but it might be a hard drive. So all these things just look like other files. And you can open them, you can write them, you can delete them, you can move them, you can rename them, you can copy them just like you do any other file. If I plug something into a USB port on a Linux machine, you get a TTY USB 0. And it's a device that's connected to that physical drive. And if I say df, I get a lot of things on here, but I also get this /dev. There's a file system under /dev/mapper, right? That's our main file system. That's where all your files get stored. And if you do this on a physical machine, you have a hard drive, you'll see like a /dev/sda1, sdb1, and so on. Those are the input, the portals to your physical drives. etc is a general directory, etc. It's where miscellaneous files go. So they're usually system files, and they include things like password, passwd, which is not the password file anymore, but it used to be just a text file. And there's information in here about networking, and there's initialization stuff for when you boot, and initialization stuff for when you log in, and so on and so forth. It's kind of a clearinghouse of useful files. And password file. Right, so like I say, this used to be the password file, and your passwords were encrypted and stored in here. And you could authenticate a user by just reading this file. That's not terribly secure, but our account information is still stored in here. So there's a username, there's a user ID, 1060, 1061, and so on. That's your unique numeric code on the system. A group ID, which is either students or faculty, your home directory, and the shell that you run when you first log in. And it's just a file. So lib is where things like standard I/O, the library, go. Lost and found is where files go when they're lost. So the file system gets checked periodically, and sometimes, you know, something doesn't get closed correctly, and you can end up with files that don't have things referring to them anymore, and they go in the lost and found area. And temp we talked about briefly. Temp is a temporary directory for files that will disappear when the system boots. And USR is the user area, but it's got a bin area, it's got games, it's got all of the include files like stdio.h and so on and so forth. So it's a hierarchy. All right, so we'll talk about doing some things in the Linux commands, so review some of the basic commands, and I want to look at a little bit of processes and ways to examine files, and work up to talking about piping commands, which is where things get real. So, all right, we'll pick up from here tomorrow.